Okay, in this class, we're going to consider Taylor series. And a Taylor series is just a more general form of a Maclaurin series. So whereas a Maclaurin series is always centered at 0, a Taylor series can be centered anywhere. So just as a reminder, because hopefully you've already seen Maclaurin series, we can use Maclaurin series to represent a function, f of x, and the Maclaurin series expansion looks like the sum n equals 0 to infinity, and then you've got your you've got your nth derivative, I guess we could call it, of the function evaluated at 0 over n factorial, and then this is x to the power of n. So that's a Maclaurin series. Taylor series is very similar. We're going to represent some function by its Taylor series just by shifting the center away from 0, so the center becomes some a value or some c value as it's sometimes written, but it's very similar. So we're taking the nth derivative, evaluating it at some a value, still over n factorial, and then we've just got x minus a to the power of n. So this just represents that shift away from a center of 0 to some more general center point a. But in terms of creating a Taylor series and creating a Maclaurin series are very, very similar. It's just you kind of in the working really as to how we go about working with these two. The Maclaurin series tends to be a little easier because you're going to be subbing in zeros for all your derivatives. It tends to be when you're subbing in a 0, the calculation is easier than if you're subbing in some other number, but process-wise are very similar to work with. There's an assumption with Taylor series and Maclaurin series that the function that they represent has to be infinitely differentiable at 0 in the case of a Maclaurin series and at the a center value in the case of a Taylor series, because this nth derivative, which I earlier almost called an infinite derivative or something, I meant has to be infinitely differentiable. So you need to be able to differentiate that infinitely many times. If you get to some point where it's no longer differentiable, then for some reason, then that's no longer possible to use a Taylor or Maclaurin series. So that's a general form. So it's useful, well, important actually to memorize that form. You should know both of these forms. So Maclaurin and then the more general form, the Taylor series. So what we're going to do is just take a look at a couple of examples. So let's say first of all that we've got the function f of x equals e to the power of 2x. And we want to develop the Taylor series for that function. So this is quite a nice function to work with because there's a nice pattern in its derivative. So remember that the first derivative we're going to be taking is the zeroth derivative, which really just means no derivative at all. It means the original function. We're going to want to evaluate that at the center. So let's say that the center for this one, let's say we're trying to develop this when the a value, the center, equals 1. So just starting off with f of x, so f of x equals e to the 2x, so that's going to imply that f of 1, so remember we're just taking the 0th derivative or the original function evaluated first of all at 1, that's just going to be e to the power of 2 times 1, so e to the power of 2, so just e squared basically. Then we're starting to build up our derivatives. And if you've already watched the video on the process for doing this for a Maclaurin series, you'll see that it's just going to be the same process. And I recommend doing it almost in this kind of almost like a table form. So you're building up these derivatives and their evaluations to get all that information first, to then put it into the series. If you try and churn out the terms of the series on the fly, if you like, then it just tends to get a little messy and easier to make mistakes. So I would definitely recommend doing it this way. So the derivative of e to the 2x, hopefully you're familiar with that. That's going to be 2e to the 2x just by the chain rule. And then that gives us f prime of 1. So we're evaluating that first derivative at 1. So 2e squared. Okay, so these e functions are really nice to work with because their derivatives just follow this very consistent pattern. This is going to be 4e to the 2x for the second derivative, so that would imply the second derivative evaluated at 1 is just going to be 4e to the power of 2, so 4e to the 2. Wanted to make that a 2e to the 2 again, but 4e to the 2, like that there. Okay, and we'll maybe just do one more. That should be enough for illustration. So the third derivative is again just multiplying by 2, so 4e to the 2x, which implies that the third derivative evaluated at 1, you can see the pattern is just going to be e to the 2. Now, it's not always going to be the case that for all functions you get such a nice neat pattern. I've chosen this one because it's a very common function to work with, and also it's a nice illustrative example. So we've got basically everything that we need here in our sort of table for this scenario. So we just need to go and start building up our series. So we've got f of x, which equals e to the 2x, and that is equal to, so the first term, which is this guy here, so that's this part. Let me just write this out in full. So it's going to be e squared over, n is 0 at this point, so it's e squared over 0 factorial, x minus 1 to the power of 0. That would simplify, obviously we'll do that on the next line. Just for illustration, we're then going to be adding to that the next term, which is this guy here. So it's going to be 2e squared over 1 factorial, x minus 1 to the 1, and then the pattern just becomes fairly obvious. We're just putting in these numbers that we already generated. 4e squared over 2 factorial, x minus 1 to the power of 2. And then, where shall I put it? The next term here, which is this guy, 8e squared over, putting in 3 this time, so 3 factorial, x minus 1 to the power of 3. And then we would just carry on like that indefinitely. So if you can simplify these, then go ahead. I mean, in most cases, you can take a couple of lines of working with these to get it fully simplified. 0 factorial is just 1. This bracket to the power of 0 becomes 1. So basically, this just becomes e squared. So that's always going to happen. Because that first power is always going to be a 0, the x term is basically disappearing, and you're just getting a constant term. This one we can drop the 1 from. 1 factorial is also just 1, so you're just going to get 2e squared times x minus 1. The next one, 2 factorial is 2. 4 divided by 2 is 2, so you get 2e squared again, x minus 1 squared. And then finally here, 3 factorial is 6, so you've got basically there 8 over 6. That would divide top and bottom by 2 to give you just 4 over 3. So it's going to give you 4 over 3 x minus 1 cubed. And then I would just carry on like that. So very, very similar if you're already familiar with Maclaurin series to a Maclaurin series, just a slight variation in how we go about the process. Okay, let's look at another example. So let's say that this time we want to take the function cosine x, which is another well-known function, another one that's good to kind of memorize the Maclaurin and the Taylor expansions for. And let's say that we want to center this guy at, let's go for pi by 2, and we'll see what we get there. So again, just starting to build up the sort of table of values, if you like. So we're going to start with our zeroth derivative, which is just the original function. So f of x is cosine x. So that implies that f of pi by 2, so testing your trigonometry here, thinking about the cosine of pi by 2, which is 90 degrees, so that comes out to be 0. So that's quite a neat result. There's a lot of zeros and ones when you're dealing with sine and cosine. So we're just going to start differentiating. So the first derivative, f prime of x, derivative of cosine is negative sine. So that would imply that the first derivative evaluated at pi by 2, sine of pi by 2 is 1, but you've got a minus in front, so that becomes a minus 1. So you might have seen this already in a Maclaurin series. What we're doing here is very similar. We're just evaluating at pi by 2 instead of 0. But we know that we get interest in sort of alternation of the terms here, just because there are sine goes to cosine, cosine goes to negative sine. So you build like a little cycle. So sine differentiates to cosine, positive cosine, but the negative in front means it'll stay a negative. So you get negative cos x. So now we're evaluating the second derivative at pi by 2. Cosine of pi by 2 is 0, so it's minus 0, which is again 0. So you're going to get this 0 every sort of second term for these. Okay, finally the third derivative, so cosine differentiates to negative sine, so it's going to be negative sine, taking you back to this positive sine, which implies that the third derivative evaluated at pi by 2, the sine of pi by 2 is 1. So you get these nice neat values. So picking up that 0 every second time, and that would happen again because when you differentiate sine, you go back to cosine. Cosine of pi by 2 is 0 again, and it just goes in that pattern. So quite a neat little expansion that. So we're then going to say that f of x, which is cosine x, has a Taylor series of the first term, which is just going to be 0, so that's actually just going to disappear. I'll just put in the 0 for the first line of working. So remember at that point, that is when this is associated with n equals 0, n equals 1, n equals 2, and n equals 3. So we're now building up the next term. So for the next term, that'll be the first derivative, so it's going to be minus 1, which is basically this part here, minus 1 over 1 factorial. So we're going to get minus 1 over 1 factorial. Again, we'll simplify that on the next line. And then it's going to be x minus our center, which is pi by 2. So x minus pi by 2. This was a power of 0. This is n equals 1. So we've got a power of 1 on there. The next term is going to be a 0 again, because we know it's just all going to be 0. And then the final term is when n equals 3. So we're back to a positive 1. So it's going to be plus 1 over 3 factorial. So you've just got to keep track carefully of this calculation. X minus, again, the center pi by 2 to the power of 3. And then that would carry on like that. So can we simplify this? Obviously, we can drop the zeros now. We don't need to write those in. 1 factorial is 1. This just becomes 1 over 1. There's a minus in front, so it just becomes minus x minus pi by 2 is to the power of 1. We don't really need that power. We can drop that. We can drop the next term. Not much we can do here. Well, you could maybe change the factorial to 3 factorial is 6, so it becomes 1 over 6 x minus pi by 2 to the power of 3. So you can start to see a pattern there, like this is a power of 1. We're assuming the next power that you pick up will be a 5, a 7, all the odd numbers, and it would continue in that fashion. Okay, so this guy here is the Taylor series for cosine x centered at pi by 2. And this guy here is the Taylor series for e to the 2x centered at 1. So very, very similar to working with our Maclaurin series, just really the question of working with the different center point. So one thing that is really important though, is not only that we want to churn out these series, but we need to know the values for which the series does actually represent the function. Is it true that any x value here allows this series representation to actually represent the function? And the same here, is it true that this series does represent cosine x everywhere, or is there some limited interval of values for which that is true? So that limited interval of values, or maybe it's all values, it just depends, is called the interval of convergence. Really, really important to find the interval of convergence for both a Taylor and a Maclaurin series. It's effectively giving you like the domain in a way. It's like when you've got a function, you want to know the function and its domain, like what values is that function valid for. In the same way, you want to find a Taylor series and Maclaurin series, but also their interval of convergence, so that you know the x values for which it is a valid representation of the function. And that's what we're going to look at in the next class. Before you get there though, just get familiar with this technique. Maybe practice a few common functions. You could challenge yourself with maybe sine x, see how sine x compares to cosine x. Maybe make it something like sine 2x or some variation and just see what you get. Practice is really important in these questions, so definitely check out a few practice questions before you move to the next class.